Swayam Prabha. Digital India. Educated India.
Welcome to the 7th lecture of the lecture series, which is on tutorials on design of transmission elements. And this lecture is on tutorial on design of worm gears. In our previous class, we studied a problem related to basics and force analysis of the worm gear. Now we are going to study the design methodology, and we will take one design related problem. We know that worm gears are used to transmit power between two non-parallel and non-intersecting shafts, and in this case very high velocity ratio can be achieved up to 100:1 in a single pair of worm gears. But the main problem with this worm and worm gear is there is appreciable amount of sliding velocity, and due to that frictional loss will be there, and due to that frictional loss there will be rise in temperature. So we must design the casing with the heat balance also. So let us start. This is in this figure a worm gear is shown with the axis of rotation of the worm, this one, and the axis of rotation of the meshing gear is this one. And in this figure, the green color axis is for the axis of the worm, and the blue color axis is axis of the gear. And in another view, the worm and worm gear is shown here. Worm is just like a threaded element, and so it will have axial pitch and lead related thing which are used in the case of power screws. In this figure, the pitch cylinder of the worm is shown with the thread on the worm, and it is obvious that this thread is inclined by an angle with the line which is normal to the axis of rotation of the worm. So the line tangent to the screw or the thread of the worm is this one, and a line perpendicular to the axis of rotation of the worm is this one. And the angle between these two lines is called the lead angle, and the lead is given by the pitch of the thread, the distance between two consecutive points on the thread is called the axial pitch px, and if number of thread or the number of start on the worm is zw, then lead is equal to px multiplied by zw, and the lead angle is obtained by expanding the screw, and this line AB is the thread length of one revolution, and this one is the pi dw, where dw is the pitch circle diameter of the worm, dw. So we are getting a right angle triangle with this length equal to pi dw, where dw is the pitch circle diameter of the worm, and this one is the length of thread in one revolution, and this angle is lambda. So tan of the lambda is equal to lead divided by pi dw, and the pitch circle diameter of the gear is shown here. This is the pitch cylinder of the worm. Worm wheel means the gear, worm gear. worm gear, and the pitch circle diameter is dg, and the pitch circle diameter of the pitch cylinder of the worm is dw. Now, in our study of spur gear teeth or the helical gear teeth, we have learned that the motion of one tooth relative to the mating tooth is primarily a rolling motion. In fact, when contact occurs at the pitch point, the motion is pure rolling. In contrast, the relative motion between the worm and worm gear teeth is pure sliding, and so we must expect that friction plays an important role in the performance of worm gearing. Now, designing a worm gear consists of the following steps. A usable decision set for worm gear mesh includes some a priori decisions in which the function should be decided. That means the power which you want to transmit, at what speed and at what velocity ratio, and the application factor. This application factor is very much similar to the overload factor which we had taken in the case of spur, helical and bevel gear. Then the design factor, that means factor of safety, ND, then the tooth system, material and processes, then a number of thread on the worm, ZW. Then based on that, some design decisions has to be taken, and those are axial pitch of the worm Px, that means the worm has these threads, a number of two. So, the axial pitch is this distance Px. Then the pitch diameter of the worm dw, face width of the gear Fg. To this pitch cylinder, a gear is meshed. When you will see the side view of this gear, then it will look like this with like this one. So, the face width of the gear is this one, F, that we have to decide. Then the face width of the worm and the lateral area of the case, that means the casing in which the worm gear set is kept, lateral area of that casing is required to be determined, because it will decide the amount of heat loss from the casing to the atmosphere. The methodology consists of a design decision is the axial pitch of the worm. Since acceptable portions are implied in terms of the center to center distance which is not yet known, one choose a trial axial pitch Px. Having ZW, number of teeth on the worm, and a trial worm diameter dw, because we have a relationship for the dw in terms of the center distance, and the center distance is a function of dw and dg. So, knowing this zw and dw, we will find from the velocity ratio the number of teeth on the gear, and then the transverse module of the gear, that will equal to axial pitch of the worm divided by pi, and pitch circle diameter of the gear, which is equal to number of teeth on the gear multiplied by the transverse pitch. Then we have a relationship which provides the range of dw, that means pitch diameter of the worm. The lower value, acceptable lower value of the pitch diameter of the worm is given as center distance to the power 0.875 divided by 2.002, and the higher value of pitch circle diameter of the worm is given by center distance C to the power 0.875 divided by 1.068. The meaning is, this is your worm cylinder, pitch cylinder of the worm, and this is the pitch circle of the gear. These are the axes, and so the center distance is this C. in terms of this C is this dW. So, it is an iterative process. Examine that your dW which you have selected is within this range or not. If it is not in this range, then from this dW lower and dW higher, we will choose a next value of dW, and then we will find the new value of center distance from the formula C is equal to dg plus dW divided by 2, and then again this C will be substituted in this and this to get the lower and higher value of dW. If the selected dW is within that range, then that W will be final. Otherwise, we will continue to do the iteration till our pitch circle diameter lies within the range given for the dW. Now, compared to other gearing system, worm gear meshes have a much lower mechanical efficiency due to sliding velocity and the loss of power. Cooling for the benefit of the lubricant becomes a design constraint, sometimes resulting in what appears to be an oversized gear case in light of its contents. That means to the amount of heat which is generated, that should be lost to the atmosphere. So, heat gen should equal to the heat loss. To make it possible, there may be a chance that we may have very big casing. So, to get the higher value of lateral area. If heat can be dissipated by natural cooling or simply using with a fan on the worm shaft, simplicity persists. So, for cooling, we may rely on the natural convection if possible, or the forced convection if a fan is mounted on the worm shaft. Water coils within the gear case or lubricant out pumping to an external cooler is the next level of complexity. For this reason, gear case area is a design decision. To reduce cooling load, use multiple thread worms, because if we have a single start thread, then we get high mechanical advantage but low efficiency. With more number of threads or start on the worm, the mechanical advantage decreases but the efficiency increases. Increase of efficiency means there will be lesser amount of heat generation or the loss of the power, and that can be achieved by the multiple threaded worm. So, that will reduce the cooling load. Also, keep the worm pitch diameter as small as possible. Multiple thread worms can remove the self-locking feature of many worm gear drives. When the worm drives the gear set, the mechanical efficiency EW is given by cos of the pressure angle, normal pressure angle, minus coefficient of friction multiplied by tan of the lead angle divided by cos phi n plus f cot lambda. Now, if gear will be the driving member, then the efficiency will be different, that we will study later on. Now, let's take a problem, design problem, which says that design a 7 kilowatt 11:1. 11:1 means this is the gear ratio or the velocity ratio mg, and this is your h, the power which you want to transmit with the worm and worm gear set. So, worm gear speed reducer mesh for a lumber mill planer feed drive for 3 to 10 hour daily use. A 28.67 revolution per second squirrel cage induction motor drives the planer feed with application factor equal to 1.25. Okay. And the ambient temperature is 21 degrees centigrade. It means T ambient, which we will use in the heat balance, is 21 degrees centigrade. The given is the power which is to be output is 7 kilowatt, because you know that in the case of worm and worm gear drive, whatever power input is given H in, the same will not come out, because due to sliding velocity and loss of power, some of the power will be lost and the H output will be different than the H in, and that will be decided by the efficiency of the drive. The design factor is taken as 1.2. Now, worm gear design is constrained by available tooling, space restrictions, shaft center to center distances, gear ratios needed, and the designer's experience. ANSI AGMA 6022-C93 design manual for cylindrical worm gearing offers the following guideline. Normal pressure angles are chosen from 14.5, 17.5 degree, 20 degree, 22.5 degree, 25 degree, 27.5 degree, and 30 degree. The recommended minimum number of teeth, gear teeth, is given in the table below. Based on the pressure angle which you will select in the first step, you will get the minimum number of teeth on the gear that will avoid the interference, and that will guide you in getting the ZG. The normal range of the number of threads on the worm is 1 to 10. Single thread will give more mechanical advantage and the lesser efficiency. As we will move for multiple thread, efficiency will increase, but the mechanical advantage will decrease. Now, let us do the selection process. As it is said that we go for the multiple thread, let us select the double thread or the double start on the worm, and so ZW is taken as 2. The velocity ratio is given as 11, and so number of teeth on the gear is mg multiplied by number of teeth on the worm, that means ZW, and it is equal to 11 multiplied by ZW is 2, and so 22. So, ZG we obtained as 22, and so let us see minimum ZG is required for which value of phi n. By inspecting this table, we found that minimum 21 number of teeth is required for 20 pressure angle. So, we will go for 20 pressure angle. So, the acceptable this number of teeth on the gear is acceptable for phi n is equal to 20 degree. So, our selection is phi n is equal to 20 degree and number of teeth on the gear is 22. Then material and process selection. AGMA relates the tangential force on the worm gear WGT to other parameters by an equation given by WGT is equal to CS, CM, CV, dm to the power 0.8 and FEG. Let us find what these parameters are, where CS is the material factor, dm is the mean or the pitch diameter of the gear, Fe is the effective face width of the gear, actual face width but not to exceed by 0.67 of the mean diameter of the worm in mm, and cm is the ratio correction factor and Cv is the velocity factor. This equation together with the factors Cs, Cm and Cv with an alloy steel case hardened worm together with customary non-ferrous worm will materials will result in lives in excess of 25,000 hours. In our problem, it was given that the required life is 3 to 10 hours daily. So, if we go for this material, the alloy steel case hardened worm and non-ferrous worm will material, then the life will be for this gear set will be more than 25,000 and that is matching with our case. The worm gear materials in the experience base are principally bronzes. So, worm gear is the gear, this is your worm and this is your gear. So, the material of the gear is principally bronzes. Tin and nickel bronzes, chilled casting produces hardest surfaces. Lead bronze, high speed applications. Aluminum and silicon bronze, heavy load, slow speed applications. The material factor Cs for the bronze in the spectrum sand cast, chilled cast and centrifugally cast increases in the same order. Now, material for the worm and worm gear are selected based on the above discussion as case hardened alloy steel for the worm and sand cast. We are using the sand cast bronze gear, means the gear is made by sand casting process and the bronze gear is selected. So, let us take the decision 1 about the axial pitch. Axial pitches for the worm are usually integers and quotients of integers are common. The typical pitches are as per AGMA 6, 7.5, 9, 12, 18, 24, 30, 36, 42 and 48, but others are also possible. So, among the given axial pitches, let us select the 36 mm. Then the axial pitch, because we know that the Px axial pitch of the worm is equal to circular pitch of the gear, and that is equal to pi multiplied by axial pitch of the worm is equal to circular pitch of the gear, and if module of the gear is known, then circular pitch of the gear is equal to pi multiplied by module mt. And that by using this relationship, we got the value of this mt, which is equal to px divided by pi. Px we have selected as 36 mm. So, transverse module of the gear will equal to 36 divided by pi, and that is 11.46 mm. Now, knowing the module, now we can find the pitch circle diameter of the gear. Number of teeth on the gear was obtained in the previous step, and that is 22. The module is obtained as 11.46, and so pitch circle diameter of the gear is 252.1 mm. Now, let us find the addendum and dedendum of the gear tooth. We know that in a gear tooth, above the pitch circle, this is your pitch circle, above the pitch circle and between the addendum circle, the height of the gear tooth is called the addendum, and below the pitch circle, the depth of the gear tooth is called the dedendum. And we have a table which gives us the dimension of addendum and dedendum based on the normal pressure angle and number of teeth on the worm. Now, in our case, we have selected phi n as 20 degree and number of teeth is less than or equal to 2. Our number of teeth is 2, and so our addendum, dedendum and hole depth will be obtained from this column. So, HA addendum is equal to 0.3183 of the axial pitch. Axial pitch is 36, and so addendum is 11.4459 mm, and the dedendum is equal to 0.3683 px. Substituting the value of px is equal to 36, we got the dedendum. And the total height or the full height is based on the axial pitch. If axial pitch is greater than or equal to 4, then this equation is to be used, and if axial pitch is less than 4 mm, then this equation. In our case, the axial pitch is 36, and so it is more than 4, and so we will use this formula. And so the hole depth or the hole depth of the, this is the hole depth of the gear tooth is obtained as 24.718 mm. Now, determination of mean worm pitch diameter, because we know that this is an iterative process. So, mean worm pitch diameter is usually chosen in the range given by equation dm, or this is dw also, because dm is used in the WGT allowable equation. So, dw is within this range, and we have not at this stage we are not having this dw. So, the mid range of this is c to the power 0.875 divided by 1.393 of this range. So, decision 2 is taken about the pitch diameter of the worm. So, let us choose a mean worm diameter dw is equal to 48 mm. Then, after choosing this dw, and earlier we have calculated the pitch circle diameter of the gear. So, now we can find the center distance, and the center distance between the axis of rotation of the worm and axis of rotation of the gear, which is this one perpendicular to the screen, is the axis of rotation of the gear. And so, the center distance is this one, and this is equal to dw plus dg divided by 2. Substituting the value of dw and dg, we got c is equal to this one. Now, after knowing the center distance, we will use this formula to get the lower value of dw and the higher value of dw. Let us find. The lower value of dw is this 150 is substituted here, and so we obtained as 40.063 mm, and the higher value is equal to, this is higher actually, higher value is 75.099, and we had selected dw is equal to 48, and it is very close to the lower value, and so the range is this one. So, let us take the some mid value of that, and that is equal to 60 mm. So, 60 corresponding to 60 mm dw, again we will calculate the center distance using this formula, and so the new center distance is 156.05. And now again we will find, after getting this new c, the range of dw. The range of dw is obtained as 41.461 and 77.72. So, the value of dw which we had taken is satisfactory, therefore, dw is chosen as 60 mm. Now, after getting the this information, we will come to the determination of lead angle. So, the lead is equal to the axial pitch we had selected, px multiplied by zw, which is 72, and the lead angle lambda, this angle is equal to 20.907. After substituting in this equation the lead and the dw calculated or obtained is 60 mm. So, maximum lead angle for normal pressure angle is given in this table. So, lead angle which we have obtained, we have to check it whether it is within this limit or not. So, for normal pressure angle of 20 degree which we had selected, the maximum allowable lead angle is 25 degree, and the calculated lead angle is 20.905, and so it is acceptable. Now, as we know that in the case of worm and worm gear, there is appreciable amount of sliding, and so we must know what is the sliding velocity, because this sliding velocity will give you the coefficient of friction, and from that we will find the amount of power which is lost. And the Vs can be obtained by the pitch circle diameter of the worm and pitch circle diameter of the gear. The pitch circle diameter of the worm will act at the pitch point in the direction of transmitted load on the worm, WWT, and pitch line velocity of the gear will act in the direction of WGT, tangential load on the gear, and this V will act tangent to the thread of the worm. So, the angle between this VW and VS will be lambda, because VW will act perpendicular to the axis of rotation of the worm. Axis of rotation of the worm is this one. And so, VW is acting perpendicular to the axis of rotation of the worm. And so, this angle is lambda. Now, to calculate this Vs, we know that Vs is equal to Vw divided by cos of the lambda. From this triangle, Vs is equal to Vw, pitch line velocity of the worm, divided by cos of the lambda. Lambda we have calculated, and Vw is equal to pi dw and nw, revolution of the worm, divided by 1000. This is RPS of the worm, revolution per second of the worm. This is the pitch diameter of the worm in mm. So, by using these two formulas, the Vs is obtained as 5.785 meter per second, and Vw similarly is this one. Vw is 5.404. Vw is equal to pi dw nw divided by 1000. Similarly, Vg will equal to, 1 minute, these two are same. So, Vw, now worm gear bending stress analysis. Because worm teeth are inherently much stronger than the worm gear teeth, they are not considered. This worm is made of a steel, but gear is made of non-ferrous material. And we have selected it as a bronze. So, in this gear mesh, this worm is stronger, and so we don't take this, we take the gear. The teeth in the worm gears are short and thick on the edge of the face. You see the teeth of the worm gear, it is something like this at the edges, and when you are moving towards the middle, then it is curved and shorter. It is curved like this because of the enveloping nature. So, at the ends they are thicker, but in the mid plane they are thinner as well as curved. So, we have to take care of these all. The AGMA relates the tangential force on the worm gear tooth WGT to the other parameters given by this, and the frictional force WF is given by coefficient of friction multiplied by Wn. While conducting the force analysis, we found this frictional force which was acting along the thread, this, and the Wn was normal to the thread. So, F multiplied by Wn was the frictional force. This F Wn is the frictional force. So, we have a relationship for the Wn and the WGT in terms of this coefficient of friction, lambda, phi n and lambda. So, Wf can be obtained from this equation 4. So, WGT, the transmitted load on the gear, the first factor is Cs, the material factor, and the material factor is given by Cs is equal to 270 plus 6.328 into 10 to the power minus 4 C to the power cube, where C is the center distance. For sand cast gears, we have to use equation 6. For chilled cast gears, this sand cast and chilled cast is the manufacturing process. So, if the bronze is made by sand cast, we have to use equation 6. If chilled cast, then we have to use equation 7. And if it is centrifugal cast gears, then we have to use equation 8. Now, we had selected sand cast bronze, and so we will use this equation, the equation number 6. So, the equation number 6 is given as this one, and the value of 6 depends on the pitch circle diameter of the gear and the center distance. Now, in our case, the pitch circle diameter is 252.1, which is greater than this 62.5, and so we will use the formula, this one, where CS is equal to 24.486 minus 6.279 log of the DG, and DG is 245.1, and thus the CS, the material factor, is equal to 9.407. Now, the next factor is the CM. The CM is called the ratio correction factor, and this is given by equation 9, and it is based on the gear ratio mg. In our case, mg is equal to 11, therefore, the first equation is to be used. Our mg is 11, so we will use this first equation. And using this first equation, the value of Cm obtained as 0.772. Then, the next factor is the velocity factor. Velocity factor is given by equation 10, and this is with reference to the sliding velocity, and the sliding velocity for our case is 5.785 meter per second. We had just calculated, and let us see where we are lying. So, Vs less than 3.56, this formula is to be used. For Vs greater than or equal to 3.56 but less than 15.24, it means our sliding velocity is lying in this range, and so we will use this formula. This formula is used after substituting the value of Vs here to get the value of Cv, and it is 0.239. Then AGMA reports the coefficient of friction F as coefficient of friction which acts between the gear tooth of worm and worm gear is given by this formula, and it is with reference to the sliding velocity again. If sliding velocity is 0, then it should be 0.15. Our sliding velocity is 5.785, and it is in this range. When Vs is greater than 0.05 meter per second, then we have to use this formula. So, using this formula, we got the coefficient of friction by substituting the Vs here as 0.0196. Now, after getting the coefficient of friction, now we can find the efficiency of the drive. Now, with the gear driving the gear set, the mechanical efficiency Eg is obtained by this formula, formula 12, but in our case, worm is driving the gear set, and so we will not use this, but we will use this formula when the worm drives the gear set. The mechanical efficiency EW is given by EW is equal to cos phi n minus F tan lambda divided by cos phi n plus F cot lambda. F we have just obtained, phi n selected is 20 degree, and lambda we had calculated. So, substituting the value of phi n is equal to 20 degree, F is equal to 0.0196, which we have just calculated, and lambda is equal to 20.905 degree, we obtain efficiency as 0.941. It means 94.1 is the efficiency of the drive. It is not 100%, it is less than that. To ensure nominal 7 kilowatt output with adjustments for Ka, the design factor, and the efficiency EW, the mechanical efficiency, considering that the magnitude of transmitted load on the gear is obtained by this formula, which is equal to 1000 multiplied by factor of safety multiplied by power output, not power in but power output, and application factor divided by pitch line velocity of the gear and the efficiency of the efficiency when worm is driving the gear set. Okay. So, substituting the value of factor of safety equal to 1.2, the power output given in the problem is 7 kilowatt and Ka is 1.25. Now, you see in the worm and worm gear, one thing is different with when we compare the spur, helical and bevel gear. In all three previous gears, the power which is given to the driving gear was important, and from that we were getting the transmitted load Wt, which was given by h divided by pitch line velocity V. Now, here as pitch line velocity for driving and driven gears are different because a Vs is coming into picture, and so we are taking the output power to calculate the tangential force on the driven gear, and the driven gear in the case of worm and worm gear is the worm gear. So, substituting these all values, we got Wgt as equal to 5406 Newton. Now, the application factor which was used in this formula and it is also given there in the problem, it is very much similar to the KO which we were using in the case of spur and helical gear. In the problem, it was given application factor as 1.25. It means the impact from the prime mover which is connected to the worm is light impact load, for example, multi-cylinder engine, and the impact from the load side of the machine, that means on the worm gear, is uniform. And so, the application factor of 1.25 was taken. Now, knowing the value of Wgt and other terms, that means this phi and lambda, coefficient of friction, now we can find the transmitted load on the worm. Transmitted load on the worm is related to transmitted load on the gear by formula 14. So, by substituting all the values, that means Gt is equal to 55,406 and phi n is equal to 20 degree, lambda is equal to 20.905, f is equal to 0.0196 and lambda is equal to again 20.905, we got the transmitted load on the worm 2195 Newton. So, you see on the worm the transmitted load is this one, and on the gear it is 5406. The worm and gear powers HW and HG are given by HW is equal to transmitted load on the worm multiplied by VW divided by 1000. That means the transmitted load on the worm WT is equal to the power on the worm divided by pitch line velocity of the worm. Very much similar formula, but here as pitch line velocity is different, and so power on the worm and power on the gear is obtained separately, and that is 11.86 is the power transmitted on the worm, and the power which is transmitted on the gear is 11.16. So, this difference will be the power which is lost, and that we can also calculate by getting the frictional force. Frictional force is given by Fwn, and substituting the value of normal load which we obtained in the first lecture, which was related to the basics and the force analysis, we get the value of frictional force as minus 121.67 Newton. So, the frictional power HF is equal to this WF Vs divided by this one. Now, face width of the gear. The AGMA equation is used to determine the face width of the gear, and the AGMA equation is this one. WGT is equal to this one. We had already obtained the CS, CM, CV and DM. So we can find the face width of the gear. So face width of the gear after substituting the value of WGT and the factors, these all, and the pitch circle diameter equal to pitch circle diameter of the gear equal to 252.1, we obtained 37.34 mm as the face width required for the gear. The worm gear face width FG must satisfy the following. Now we have to check the determined face width is within the allowable limit or not. The allowable limit for FG is the face width of the gear is related to the axial pitch. If axial pitch is greater than 4, then this one. If axial pitch is less than or equal to 4 mm, then this formula. In our case, as Px is equal to 36, and so we will use this formula. Using this formula, we got Fe as within this to this. This is the calculated one, and from after substituting this 36, we got this 40. And so the effective face width is taken as 38.0 mm from this range. So effective face width of the gear is 38 mm. Now the AGMA equation for tangential force on the worm gear teeth is this one. With all factors determined, with the determination of this CS, this all, the W tangential allowed has come as 55.02 Newton, and the WGT which was determined is equal to 5406 Newton. That means the maximum allowable tangential load on the gear is 5502 Newton, but which is acting is 5406 Newton, which is lesser than the maximum allowable. So this is little excess capacity. The force analysis stands. Now, as we know that in the case of worm and worm gear, there is appreciable amount of heat generation. So we must do the thermal analysis. So here the efficiency of the drive when the worm gear was driving came as 0.941. So we will use that to get the power input or the input power. Input power is the power of the worm, HW, and HW we have calculated as 11.86 watt. And we have the heat loss rate Q dot from the worm gear case. That means if the casing is this one, within which the worm and worm gear set is kept, then the heat loss will equal to 1000 1 minus EW. EW is the efficiency of the worm drive, and H in. H in is this one. So we will find the heat loss rate Q dot. The overall heat transfer coefficient U for the combined convective and radiative heat transfer from the worm gear case in watt per meter square per degree centigrade is given by this formula. When no fan on the worm shaft, that means only natural convection is there for the transfer of heat, and when fan on the worm shaft is there. Now let's choose air cooled, no fan on the worm, then we will use this formula to get the value of capital U. So overall heat transfer coefficient is given by this NW. NW is the revolution of the worm, which we had obtained as 28.67 divided by 1.7165 plus 8.2 is equal to this one. This is the overall heat transfer coefficient for this casing. Now knowing that, we will get the Q dot. Q dot is equal to 1001 minus EW and the H in. H in is this one. Okay. Now the required area for the transfer of heat will is given by AGMA as A minimum is equal to 1.139 10 to the power minus 4 C to the power 1.7. So, substituting our C, which we have calculated as 156.05, the minimum lateral area required for transfer of heat is obtained as 0.6096 meter square. Now, expect an area of 0.7. This is 0.6096, we have taken as 0.7 meter square lateral area. Now, the temperature of the oil sump Ts is given by, that means here you have a gearing system and the oil sump is there, okay, and in this oil sump the temperature is Ts and the outside temperature is Ta, and the temperature of the this block is Tb. Okay, so we can find the oil sump temperature with this formula. Q dot is equal to overall heat transfer coefficient and the lateral area of the casing multiplied by Ts, which is the average temperature of the lubricant, minus atmospheric temperature. So, using that we got Ts is equal to temperature of the this sump is equal to Ta plus Q dot divided by UA, overall heat transfer multiplied by lateral area, and so we got the lubricant temperature, and the lubricant temperature came as 61.65 degrees centigrade. So, lubricant is safe because it is lesser than, it is not very high, and so the lubricant is safe with some margin of smaller area. Now, worm gears bending stress analysis, which is an alternative method. So, Buckingham get this sigma is equal to WGT divided by Pn FEGY, where Pn is the axial pitch multiplied by cos of the lead angle and Y is the Lewis form factor, which can be determined from this table depending on the pressure angle selected. In our case, it is 20 degree, and so Y is equal to 0.125. So, substituting that, we get the value of sigma as 33.80, but the allowable value of sigma is equal to 55.0 to 5,502 Newton, and so it is okay. Now, for the case of wear analysis, again Buckingham gave the wear load, and the wear load is given by W, the tangential load on the gear allowable is equal to Kw, pitch circle diameter of the gear multiplied by face width of the gear, where Kw is the worm gear load factor, and this worm gear load factor Kw can be determined from this table based on the material of the worm and the material of the gear. In our case, material of the worm was hardened steel and the material of the gear was bronze, and the pressure angle was 20 degree, and thus our Kw is 0.551. So, using this 0.551, we will get the transmitted load allowable as per the wear load, or considering the wear, is equal to 0.551 multiplied by dg, the pitch circle diameter of the gear is 252.1 and Fe is 38. And so, for considering wear, the allowable tangential load is 5,728 Newton. But the tangential load which is acting on the gear is only 5,406 Newton, which we had calculated in our previous slides. It means this is allowable. Considering wear also, the allowable load, tangential load, is bigger than the tangential load which is acting on the gear. So, the method of Buckingham does not have refinement of the AGMA method, but it gives some substantial information about the wear load, and here it is visible also. Following references were used in this tutorial on design of worm and worm gear. And in this design problem, some of the parameters were given, like it was said that the gear has to transmit power in the ratio of 11:1 and some other information. Based on that, first we selected the axial pitch and thereafter we found the different factors of the allowable tangential load on the gear and the tangential load which is acting on the gear, considering the power output H0 which was given in the problem and taking consideration of the efficiency of the drive when the worm was driving and the factor of safety and the application factor. We also studied, as per Buckingham, what will be the maximum allowable tangential load on the gear considering wear. And we found that the maximum allowable tangential load on the gear considering wear is more than the actual tangential load which was acting on the gear. And therefore, in the case of bending and in the case of wear, our worm and worm gear drive has satisfactory parameters which were determined during the design process. Thank you.
Understanding oneself, understanding others, understanding society at large, understanding the nature, these are all driven by basic human curiosity. We would all love to understand why things happen, what happens, what is the final outcome, why certain things fail. These are all exercises that we perform in various domains of knowledge. Therefore, knowledge in various domains, you would realize they are actually social artifacts. They have to be rooted into historical perspective, they have to be culturally salient, and there would be socio-political reasons behind this. Whether you talk with respect to engineering sciences, whether you talk with respect to physical sciences, biological sciences, social sciences, that's the reason why humanities and social sciences should be understood by all of us. The knowledge that is segregated, that is divided with respect to areas, specializations, all of them needs to be understood in its context. And what provides the context? It is the social reality. How do you correlate knowledge in a given domain with the cultural reality, with the social reality, with the socio-political compulsions? Okay, how do you understand the law of nature, okay, in its totality? And for doing that, you require the understanding of humanities and social sciences. Say for instance, if you are trying to understand the effect of a particular bacteria, a virus, any microbe, how it affects behavior, how it affects the organism, human being, you start looking at it from a pure biological point of view. If you are trying to look at a particular type of a wavelength, say for example, you are emphasizing on the understanding of the effect of radiation on human life, you are looking at things from a physical point of view. You are looking at the corresponding changes inside the body, you are looking at the physiological side of the understanding of the information. You are trying to understand why, despite knowing the risk that is inbuilt in the process, why still human beings engage into it. You are looking at it from a pure behavioral point of view. Why society at large admire things which has full of risk. You are trying to understand things from a pure sociological point of view. Why people use particular set of words to explain those experiences. You are trying to understand things from the linguistic point of view. So, there are whole lot of things, and then finally you try to combine all of them to say that what are the guiding principles in life. Then you say you are looking at life, you are looking at humanity from a pure philosophical point of view. And this is what social sciences courses provide you. They provide the context to you in which you would be finally positioning the understanding of the knowledge in any given domain. It could be engineering, it could be sciences, it could be medical sciences, it could be social sciences stuff, it could be humanities stuff. So, contextualizing the knowledge is what humanities social science courses help you obtain.